All right, guys, this is 3.7, the chain rule. Sorry, I'm not there again today. I know, I'm sad too. My daughter has strep throat. Yay. So we have her on some antibiotics, and I'm also sorry that this lecture didn't get posted sooner. But we had to go to the doctor. So, oh my goodness, sickness. It's crazy. That's the thing with having kids is they just are little germ factories, and they just spread it around to everyone, and they share each other. Like my son was licking Eliza's face yesterday, and she was laughing and letting him do it. So anyway, this is what happens. All right, so we're going to do 3.7 today, which is the chain rule. Once I state the chain rule for you, I'm probably not going to prove it for you. Maybe I'll do that on Friday in class. But what I really want is you got to know how to use it. So I just want to do a bunch of examples for you. And I really like the way your book gives you kind of two ideas. Well, there are two ideas, two notations for the chain rule. Not two ideas, they're exactly the same thing, but two different notations, because remember we had our two different guys who are credited with creating calculus, so we have different notations. But let's kind of talk about the motivation for the chain rules. So let's consider a function like f of x equals, I don't know, 4x minus 1 squared. Okay, so right now, the only way that we can take the derivative of this is to FOIL this out. Because if you thought, which maybe you think you can do this, if you thought to yourself, but look I have an exponent here, right? And I know what to do with x squared. If I were to take the derivative of x squared, I know what to do with that because my teacher proved that to me, kind of. I'm going to bring the 2 down. I'm going to take 1 away, right? So what if I do that with this function also? I'm just going to pretend like, I have something raised to the squared or raised to the second power. So why don't I just also bring the 2 down, right? And take 1 away. Well, let's see. So what would we get for the derivative? Then that would be 8x minus 2. So let's see if that actually works. Well, if we look at what we know we can do, so we know f of x, and this kind of is how we talked about, remember, the product rule. I know that I can FOIL this out, and we believe in foiling, right? So we know if we FOIL this out, that'll be 16x squared minus 4x will give me minus 8x, and then plus 1. So if I take the derivative of this now, and you all agree, and you're agreeing with me, in my mind, you're all agreeing with me right now. If I take the derivative of this guy right here, right, which we all agree that this is true. We just FOILed it, right? We haven't broken any rules. The actual derivative is 32x minus 8. So that's a problem. That's a problem because here I said that the derivative was 8x minus 2 by just bringing that 2 down. And here, what do I have? I have that the actual derivative, which what we know is 32x minus 8. So why the discrepancy? Well, when we made this assumption, right, that we could just bring the 2 down and take 1 away, remember the power rule right now is for x to the nth power. It's not 4x minus 1 to the nth power. It's not 5x plus 17 to the nth power. It is just x to the nth power. So that power rule is just nx to the n minus 1 as long, there should be a 1, as long as we just have an x here. Guys, you can't just assume things. We know what assuming does. We can't just assume, right, that rules like this carry over to situations that aren't defined the same. So when we deal with something like this function right here, if you notice between these two things here, what's the only difference really? Well, this guy, this guy really is this one. It's just multiplied by 4. And where is that 4 going to come from? It's going to come from that inside function right here. So remember, I'm not just taking x to a power. I'm taking 4x minus 1 to a power. Also remember that the derivative is a rate of change. So when I do the power rule where I bring that 2 down and take 1 away, basically what we're doing with that power rule is we're saying, okay, this is how the squared function, right, in this case a squared function, is that is what the derivative with that squared function, again, no sleep again last night, the squared, I have excuses. As many as you need, I have excuses for not knowing what I'm saying. The derivative, I've accounted for the squared function and how that squared function makes my function change, right? Or my derivative takes into account the change of that function by bringing the 2 down and taking 1 away. Well, now though, what we have to also consider is we have to consider what's happening on the inside. The derivative of the inside is also going to influence the derivative of the whole function. So when I do the power rule, that's accounted for how that function, something squared, right, is changing. Now what we're going to see is we need to multiply by the derivative of whatever that inside function is, because I'm not just taking x squared now, I'm taking 4x minus 1 squared. And so that inside function, that 4x minus 1, okay, that inside function, that is also changing as x changes, right? What is 4x minus 1? How is that changing as x changes? What is its derivative? It's 4, so we have to multiply by that 4. These colors are getting a little crazy. And notice if we did multiply by that 4, I actually do get the derivative that I know is true, okay? So let me give you another, I really like this example in your book. So let's say we have Yasmin. I know these are kind of silly names. Ursula. I looked up how to spell this. Ursula or Ursula. I'm trying to find UYN. Hold on. Oh yeah, Ursula. Apparently I'm in a Disney phase here. And let's do an X, right? So let's say that we have Yasmin, Ursula, and I don't know, Xavier. That's not how you spell it. I don't, you know. My kids aren't, well, Eliza has a Z in it, but Xavier? Sure. Xavier. Let's say that we have, this is just kind of silly, but it's also kind of fun. Let's just say that we have 3 people, okay? And I really like this example in your book. I think it's kind of a cool way to explain why the chain rule works that isn't mathematical. Well, it's a little bit mathematical, but it's not exactly math. So let's say that and your book totally is taught, I'm stealing this from your book. They use Yancy, Yuri, and Zane, but I'm going to use these guys instead. So let's say that they are picking apples. All right. And here's a couple things that we know. We know that Yasmin, okay, so they're picking apples. We know that Yasmin picks apples, okay, 3 times faster. 3 times faster. Okay, 3 times faster than Ursula. Okay, so we know that Yasmin picks apples 3 times faster than Ursula, and we know that Ursula picks apples twice as fast, or 2 times faster. So Ursula picks 2 times faster than Xavier. I hope that's how you say it. So what I want to talk about when we're, this seems like a stupid example, but this is actually really cool. So if I'm talking about Yasmin picks 3 times faster than Ursula, I want to describe that as a rate of change. So I'm going to call that dy, right? That's the change in Yasmin or how fast Yasmin picks apples. With respect to Ursula, right? That's what that would be. That's the rate of change, the rate at which Yasmin picks apples with respect to how fast Ursula picks apples. And what would that rate of change be? It'd be 3, because I know that Yasmin picks 3 times faster than Ursula. And then if I think of this one, right, Ursula now, so that would be du, right? The rate of change of Ursula is 2 times faster than Xavier, so dx. So the rate at which Ursula picks apples with respect to how fast Xavier picks apples is going to be 2. It's 2 times what Xavier does. So what if I wanted to know the rate of change then of Yasmin, right? How fast does Yasmin then pick with respect to Xavier? So that's the question here. So if I know how fast Yasmin picks with respect to Ursula, I know how fast Ursula picks with respect to Xavier. How much faster then is Yasmin versus Xavier? Well, that's going to be the rate at which, Yasmin is 3 times as fast as Ursula, but Ursula is 2 times as fast as Xavier. So what do I know about Yasmin versus Xavier? We know that's going to be 3 times 2, or it's going to be 6, okay? So what this is showing right here is this idea, it is another idea of the chain rule. Okay, this guy right here is saying that dy, the rate of change of y with respect to x, can be thought of as the rate of change of y with respect to u times the rate of change of u with respect to x. And that is our Leibniz notation, right? Not our Newton notation. Remember, he was a little bit more formal with notation and thoughtful with notation. So this notation is really, really useful for us. We're going to see that when we do implicit differentiation. It's very useful for us when we move on to other functions. So this is one form of the chain rule. We're going to write this down here in a minute, right? And what this really says is if I want the rate of change of y with respect to x, I can find the rate of change of y with respect to some function u, and then I multiply that by the rate of change of u with respect to x. So like in this case up here, the u is going to be the inside function, or excuse me, the u is going to be the outside function. I'm sorry. The u is going to be the inside function, and then kind of the y is kind of the outside function. We're going to do lots of examples, don't worry. One other way to think of the chain rule, okay, another way we can think of this that doesn't involve apples at all is that we're going to use the chain rule when we have a composite function. And so we'll write, don't worry, we're going to write the chain rule down completely. But if you remember from college algebra, right? Remember being in a fog sometimes? In college algebra? A fog in college algebra was f composed with g of x. And what that was is I have an outside function f and I have an inside function g. So just like, careful, this is going to be a little weird. This guy right here is is an example of a composition of functions. My outside function is something squared. My inside function is 4x minus 1. So if I have something like that, that's when we must be using the chain rule. So the chain rule, if I take the derivative, if I think of this function, okay, and if I think of this inside function, I'm going to call u g of x, okay? So then the derivative of this composition, f of g of x. Wow, I have way too many parentheses there. Come on, go away. Oh, no, I didn't. Yeah, there we go. Okay, f of g of x, right? I can think of this as the derivative then of f of u. I'm not saying anything bad there. This is just a function of u, okay? And so what the chain rule is going to tell me to do is to take the derivative of my outside function, so f primed, evaluated at u, but then the chain rule forces us to have on the inside the derivative of g. And that's going to be my derivative. And another way to think of that, if we think of this in the Leibniz notation, this is my dy dx, okay? This is the derivative of y with respect to u. Notice it's that inside function. And then this is du dx. And of course, if I took the derivative of u, that would be du dx, and that would be that g prime of x. I feel like maybe I'm confusing you, even though I don't have anyone here. My cat looks extremely confused by what I'm saying right now. Why don't we write this down? Let's write the chain rule down, and then I just want to do a bunch of examples, and we're just gonna do what I want, because you can't. I guess you could fast forward me and I wouldn't even know it. That'd be so sad. Okay, so let's write down the chain rule. I am not going to prove this for you. Again, maybe I'll prove it for you on Friday, but I'm not going to do this on the video. So if you can't sleep tonight because you don't know the proof of the chain rule, it's in your book. It's at the end of section 3.7. So go ahead and go ahead and read that. It'll put you right to sleep, promise. All right, so let's suppose, so a couple things here. Let's suppose that f is a composite function. It doesn't even have to be a composition of functions, but we'll just say it's a composition of functions. So it's f of some function u, and let's say that it is differentiable. Okay, so I know I can take its derivative at u equals that g of x. That's my inside function, okay? And we also need, we're gonna have to multiply by the derivative of the inside, right? So we need that function g of x, which we're calling u. Let's say that it is differentiable at x. Okay, so basically, like, we're gonna have nice stuff happening. Wherever we're gonna take this derivative, let's just have nice stuff happening, right? No cusps, no corners, anything like that. We want it to be differentiable. Then the composite function, so if I just plug that u in, the composite function y equals f of g of x, right? Which we've defined g of x to be u. So f of g of x is differentiable at x. If these guys are playing nice with others, then this guy's going to play nice with others, right? And the derivative is given by, and we'll have two notations here, or is found by the following. Okay, so two notations. First, if I want the rate of change of y with respect to x, I take dy with respect to u, right? So that's this form right here. That's the derivative kind of my outside function. And then I need to multiply by the derivative of the inside function, which is du dx, okay? Now these are differentials. These du's technically don't cancel out, but you see, you could cancel them out if if we really were in the rational numbers, we could cancel those out. We can't actually do that, but we could. Or the other way of thinking of this is if I take the derivative of f composed of g of x, and this is probably the way that you will think of it mostly, but this notation is really important, and we're going to use this notation more later on. So I want you to be comfortable with both. But this is the way you really probably are going to think of it. If I have a composition of functions, this is how I say it. I take the derivative of the outside, I leave the inside, and then I multiply by the derivative of the inside. Take the derivative of the outside, leave the inside alone, then multiply by the derivative of the inside. Here's the important part with the chain rule. That inside stays, okay? So it's not that you're taking the derivative of the outside and then you're putting in the derivative of the inside at the same time. You're taking the derivative of your outside function, leaving the inside alone, and then multiplying by the derivative of the inside, okay? Let's do a couple examples. So they have a procedure in your book. You're welcome to look at that. I think it's on like page 192. You can write that down if you'd like. I'm not going to. I'm just going to do a bunch of examples for you. So we're going to practice using both notations. So let's first practice using the Leibniz notations, the dy dx's, okay? So for example, let's find dy dx. And let's start off with that first example that I did, okay? Y is equal to 4x minus 1 squared, okay? I have a composition of functions. I could FOIL this out. You could, but now we're going to see we're going to have other functions that we're not able to FOIL out, okay? So what we want to do is we want to find what is our outer function and what is our inner function, okay? So if you look at this, I am going to define my outer function and my inner function, and then I'm going to use the dy du times du dx. So if you notice, okay, most of the time, this isn't always true. This isn't always true. A lot of the times, though, your inside function is going to be everything inside the parentheses. So I'm going to set u equal to 4x minus 1. Okay, and so look at what happens if I let u equal 4x minus 1. Then what does y become? Y becomes u squared. And then again, I'm just going to write that u next to it. And u is 4x minus 1. And remember what our chain rule says. Let's write this up here so we remember it. dy dx, right, is dy du times du dx. And then after, we don't want any u's in our final answer though. We're going to get some u's in this answer, and then in the very end we're going to substitute back. So look at what this is saying. This is just saying to take the derivative of y with respect to u. So now that I have made that substitution, right, now that I've kind of undone the composition, I'm letting u be the inside stuff. I'm going to take dy dx is going to be equal to dy du. So that means take the derivative of this with respect to u. Well, what would that be? That would be 2u, right? Because it's with respect to u. And then what did we want to multiply by? The derivative of u with respect to x. So what's the derivative of u with respect to x in this case? It is 4. That's what the chain rule says. This is the derivative of my outside function, right? This is the derivative of my inside function. And now the last step is I want to replace that u with what I had set u to be in the first place. Because if we started with a function with x's, we want to end with a function with x's, right? We're just kind of using this u notation to use the chain rule and to kind of see that composition, okay? I hope that makes sense. Let's look at another one. It's tough when you're not here to stare at me, you know, blankly. No, I tease you guys. You guys don't actually. Not all of you stare at me blankly. Some of you stare at me blankly, but there are quite a few of you that don't. So that's good. Some of you look at me with tears in your eyes. I'm just kidding. Just kidding. That's a joke. Let's say we have 1 over the cube root of 5 minus 6x cubed. Okay, so the one thing here is what I want to do is actually I don't want a cubed, I want a squared, just so we don't get the 3's too mixed up. The first thing I'm going to do here is I'm going to rewrite this as 5 minus 6x squared all to the negative 1/3. Okay, because it's in the denominator, it's negative. It only becomes negative if it's in the denominator. Okay, and the reason I want to do this is it kind of helps me see what my u is going to be. Now, I could have actually left it like this, and I could have let my u be the 5 minus 6x squared, which is what I'm going to do, and then left this as 1 over the cube root of u. But I think it's just easier to write it like this first. Now, I'm going to let u equal 5 minus 6x squared. That's going to be my inside function. What does that mean y is then? If I replace this whole thing with u, y is u to the negative 1/3. Okay, and then what does my chain rule say? dy dx, right, is going to be equal to dy du. So I'm going to bring the negative 1/3 down. I'm going to take 1 away. Remember, 1 is the same as 3/3, so that would be a negative 4/3. And then what does the chain rule say? I want to multiply by the derivative of u with respect to x. So in this case, the 5 goes to 0. 2 times negative 6 is a negative 12. X, take 1 away. Okay, and now we can simplify this a little bit. Negative 12 divided by negative 3 is 4, right? And then I want to rewrite this u. So what do I have in the numerator? That 4x is going to stay in the numerator, right? Because it has a positive exponent. And then this negative 4/3, it says I'm in the wrong place, so I'm going to put it in the bottom. But instead of having a u, I'm going to come back to what I defined my u to be, which was the 5 minus 6x squared. So I have 5 minus 6x squared. Sarah, you should write what you say. 6x squared all to the 4/3. And that's my derivative. Isn't that neat? I know you think so. What's nice about when I make these lectures is I just pretend you're talking to me. And I pretend that you're enjoying yourself. And so it's a pretty good deal. Right? All right, let's do like 2 more maybe with this type of notation, and then we'll go to the other notation, which honestly, the other notation is probably what you're going to use more. We want to get to where we're feeling really, really comfortable with the chain rule, and we don't really want to have to go and do like the u substitution every single time, but it's very good practice to do this. All right, so part C. I'm going to steal this one from your book. Well, it's one similar to it. Let's look at y equals cosine cubed of x. Okay, here's one thing when you're first learning the chain rule, I really, really recommend, it's tough sometimes to see what your outside function is and what your inside function is. So whenever you have a trig function that's being raised to an exponent, okay, so whenever I have something, something like this, what I really recommend until you get comfortable with this is, what is cosine cubed of x mean? That means the cosine of x cubed, right? That is what that means. Those are exactly the same thing. And if I write it like this, it's a little bit easier for me to see what my inside function is and what my outside function is. So I'm going to let u I'm going to let u equal cosine of x. Okay, so what does that make y then? Y is just going to be u cubed. Okay, u is still cosine of x. Right? I need to get rid of this. Oh, come on. There we go. Hold on. It's bothering me. Okay, while I'm doing this, see if you get what, do the answer for me really quick. All right, so now that we have that cleared, dy dx then, again, is going to be dy du. So I'm going to take the derivative of this with respect to u. So that's 3u squared times the derivative of u with respect to x, which is a negative sine of x. And then because I started with a function with only x's, I want to end with a function with only x's. So this would be 3 cosine of x squared times a negative sine x. This notation is horrid, though we never put stuff like that. So I'm going to put my negative in front. So I would have a negative 3. We'll put sine x first just because it doesn't have an exponent. And then cosine squared x. And that's about it. And that's my derivative. Isn't that cool? What would be different if we had y equals the cosine of x cubed? Ooh, things just got interesting. So I'm going to get some parentheses in here again. This is the cosine of x cubed, right? So because the cubed isn't after the s, that means I'm taking the cosine of x cubed. So I'm going to let u equal the x cubed. I'm going to let u equal the inside stuff. So this is going to be the cosine of u, and then I'm going to let u equal x cubed. So again, then dy dx, right, is going to be the derivative of y with respect to u. So if you notice on all of these, when I take that derivative of y with respect to u, what I'm taking is I'm taking the derivative of that outside function. Okay, and that's going to be important when we think of our next notation. So I'm taking the derivative of the outside function and I'm leaving the u alone. That's the idea here. So the derivative of cosine is going to be a negative sine of u. This is the the derivative of y with respect to u. Then the derivative of u with respect to x is 3x squared. And then I'm just going to replace my u and kind of clean this up a little bit. Bring the 3x squared in front. So I have a negative 3x squared sine of x cubed. Okay, and you technically probably don't need the parentheses around x cubed. I just really like to put those to make sure my reader understands that I'm not cubing the sine, I'm cubing the x. Okay, so let's look at the other way. So by the other way, I'm talking about, whoops, I'm talking about this way right here. Okay, so let's clear this out. Oh my goodness. Oh my goodness, my cat keeps wanting to go out of my room to see Anna and then wants to come back into my room. Hold on, I gotta let her in. All right, so what I want us to find in this example, same idea, okay, find the first derivative. I'm not using the dy dx notation now because I want to use the other notation. So let's find the first, oh, I meant to grab my eraser there. So remember, right, the dx of f of g of x, right, equals the derivative of the outside, leave the inside. That's that u times the derivative of the inside. So let's start off pretty easy. Let's say I have a function, I'm not even going to call it f of x right now. Let's just write down the function. Let's say I have 4x to the 5th minus 2x squared plus 7, all raised to the 8th power. So if I didn't have the chain rule for this, oh man, you'd have to multiply this all out. I mean, it'd be a good time. What else would you do, right? Do something productive probably. So here's what the chain rule says. So what you want to think about is, what is my outside function? That's what you need to identify first. And then what is my inside function? So again, it's pretty easy to see that here, I think. So my inside function is there in purple. That's going to be that 4x to the 5th minus 2x squared plus 7. My outside function is going to be something raised to the 8th power. Okay, so the derivative of this, so d dx of 4x to the 5th minus 2x squared plus 7 to the 8th. You know what? I'm just going to call it y. I'm trying to avoid using the f of x because I don't want to confuse you, but I feel like you'll be fine. Let's call this h of x then. Okay, so the derivative of h then. Again, take the derivative of the outside function. So if I had x to the 8th, right, what would the derivative of that be? It'd be 8x to the 7th. But instead of having an x there, I want to put my inside function. So this would be 8 times 4x to the 5th minus 2x squared plus 7. Do not take the derivative of the inside, okay? So you take the derivative of the outside, leave the inside, and then my chain rule says multiply by the derivative of the inside. Again, the derivative is a rate of change. So when you bring this 8 down and take 7 away, this part right here is accounting for how this function changes with respect to power something to the 8th power. Then I multiply by the derivative of the inside, making sure I have parentheses because my derivative is going to involve more than one term. So what do I have on the inside? It would be 20x to the 4th minus 4x. And I think you could probably just leave it like that. I mean, what else could we do? Maybe we could factor 4x out of this and multiply it by the 8. So I would have 32x. Take a 4x out, that would give me 5x cubed minus 1. Yeah, let's go ahead and do that. Again, we're all gearing up for in chapter 4 setting these suckers equal to 0. So it's good to see it in factored form. And now we're done. Okay. So again, I took the derivative of the outside, I brought the 8 down, leave the inside, take 1 away, and then multiply by the derivative of the inside. Okay. What about if I had h of x equals the square root of x minus x to the 4th? Okay. So I'm going to so one thing that you're going to want to do is you're going to want to think of this as a power rule, right? If I had the square root of x, I would think of that as a power rule. So the first thing I usually do with something like this, and just like I did that with the cube root on the bottom in the last example, I'm going to think of this as x minus x to the 4th all to the 1/2. Not negative 1/2 because it's not in the denominator, just 1/2, okay? And now let's take the derivative. So h prime of x. What is my outside function? Again, this is a composition of functions, so I must use the chain rule. The outside function in this case is the power rule. My outside function is to the 1/2. What is my inside function? It's x minus x to the 4th. So the chain rule says take the derivative of the outside and leave the inside. So the power rule tells me to bring my exponent down, leave the inside, and take 1 away. That would give me a negative 1/2, okay? Bring the 1/2 down, leave the inside, take 1 away. Don't forget to take 1 away. I say these things because I know it's something that students do. And then multiply by the derivative of the inside. And then what's going to go in the denominator here? This guy's not going in the denominator because it has a positive exponent. Remember, you have to have parentheses around that. But this guy is going into the denominator. This is 2. And then I could leave this as raised to the 1/2, or I could write the square root. I will accept either one. And that's what we got for the derivative. Again, bring the exponent down, take 1 away, leave the inside, and then multiply by the derivative of the inside. Okay, let's do a couple more. Oh, whoops, I didn't mean to do that. I did mean to do this, though. What if we had something maybe a little bit more, I know you hate it probably when I say something a little more interesting, because that means we're probably going to do something a little bit harder. But this is are we on C? I think we're on C. What about, I'm still just going to use h of x because I'm lazy. H of x equals cosine x all over 1 minus sine x cubed. Oh man. This one I have a feeling we're not going to be simplifying too much, but you never know. So what's my outside function? Again, my outside function is the 3, right? What's my inside function now though? It's this cosine of x minus all over 1 minus sine x. So when we talk about these rules that we have for differentiating, what we want to think about is like, what's my overall outside rule? And then what's a rule that might come up as I work with that outside rule? So my overall outside rule here is going to be the chain rule. And then within the chain rule, as I dig into the chain rule, what's some stuff I'm going to see? Looks like I'm going to see the quotient rule, right? And then inside the quotient rule, I'm going to have some trig functions, some trig derivatives. Okay, so my outside functions, my outside rule is a chain rule. So again, what's my outside function? And this is obvious, right? It's the third power. So I'm going to bring the 3 down. I'm going to leave the inside. And I'm going to take 1 away. Okay, and then I'm going to give myself a little bit of room here. Now, what does the chain rule say I have to do? I have to multiply by the derivative of the inside. So remember, I brought the 3 down, took 1 away. I leave the inside. Now I multiply by the derivative of the inside. So I'm going to do a little bit of quotient rule. I mean, why not? So we're going to do a little bit of down, d up. I'm going to run out of room. Minus up, d down, negative cosine, right? All over down, down. And then this will be fun. We get to simplify this. So let's see how we're going to simplify this. So first, I'm going to put my 3 in the numerator because that's 3 over 1. I'm going to have a cosine squared x, right, all over 1 minus sine of x squared. So I just took that squared and applied it to the top and the bottom. And then in the top here, let's take that negative sign through. So I get a negative sine x, and I'm going to have plus sine squared x. Oh, this is pretty great. Oh, whoops. And then plus cosine squared. Oh, this is so cool, you guys. And then this is going to be all over. Oh, this is so neat. 1 minus sine x. I just made that up. I must have, in my mind, had seen maybe what this is. I'm going to leave this here because I see some cool stuff is about to happen. What's sine squared plus cosine squared? That's 1. So this whole thing here is 1. So notice on top what I get. I get 1 minus sine x. That is so cool. All over 1 minus sine x quantity squared. So now I can cancel one of these whole things with this. And so what's my final answer? All of that work comes down to 3 times cosine squared all over. I have 2 1 minus sine x's times another one. I'm going to have 3 of them. And then that's it. So you can see, so in my trig class right now, I'm teaching simplifying trig or expressions involving trig and proving identities. And as much fun as those aren't sometimes to students, they're quite important, right? To get those skills of simplifying trig expressions, because look at how nice that is now. Now, if I need to work with this derivative any further, set it equal to 0, set it equal to a different number, do anything with it, it's much nicer in this form than if I had left it in something ugly like that. Okay. All right. I want to do one more example. Now, this is a big one. And this is one that, did I say one more example? Not quite sure how, maybe one more, maybe a couple more after this. I don't know. Let's see where we're at. We're at 37 minutes. Yeah, we should probably wrap it up pretty soon. Was that D? Sure. Insert the next letter in the alphabet here. I'm going to put E. I'm not sure. Which, no, I think that we're at D, right? I don't know. Doesn't matter. Let's put D. I think we might be D. It doesn't matter. What I want to look at is a function like this. So this one's a little bit trickier to see, you guys. So what if I had h of x equals e to the 5x? So when we're dealing with E's a little bit harder to see. So all these ones that we've done up until now, right, have really had, it's been kind of easy to see what your inside function is, because mostly it's whatever's in the parentheses, or it's whatever is underneath the root, or maybe it's whatever you're taking the sine or cosine of, right? So it's kind of easy to see that, whereas something like e to the 5x is not quite as easy to see. But what I'm going to do is I'm going to consider, and I'm going to use some u here, I'm going to consider u to be 5x, okay? So when you're dealing with e is actually going to be your outside function, because now f of u is e to the u. Do you see how e then is my outside function? Now remember, what is the derivative of e, you guys? It is just e. You just rewrite it. Okay, so when I take the derivative of e, when I'm using the chain rule, I want to think of e as my outside function, and then whatever is in the exponent, that's going to be my inside stuff. So the way I remember this with e is I just rewrite it. That's the derivative of the outside, and then I multiply by the derivative of the exponent. Okay, so there's the derivative of my outside function. This is the derivative of my inside function. So my final answer is just 5e to the 5x. I'm gonna do another one. H of x equals e to the tangent of x. Okay, so again, my outside function when I'm dealing with e, if it's only e, if it's just e is my outside function, so I'm just gonna rewrite it. Okay, rewrite it and then multiply by the derivative of the exponent. Okay, rewrite it. This, my friends, is the derivative, is that f primed of g of x. And then this right here, that secant squared, is my g primed of x. Apparently I'm just going to keep going. What if instead of e to the tangent of x, what if I had the tangent of e to the x? This is cray. Do you say that anymore? I don't think you guys say that anymore, you cool young people. All right, outside function. In this case, it's pretty easy to see, I hope, that my outside function is tangent. So what is the derivative of tangent? That's secant squared of e to the x, right? Leave the inside times the derivative of the inside. So this would be e to the x times the secant squared of e to the x. That one's a little funky looking, but I hope that makes sense. That one just reminded me of one that I want to do for you really quick, and then I promise I'm going to be done pretty soon. Maybe. Find dy dx. So now you can use either notation. What if I had y equals, let's say the cosecant of 4x squared? Okay. I want to look at this one in terms of the dy du really quick, because if you look at this one, I'm going to let u equal 4x squared. Okay, so if I let u equal 4x squared, then what is y? Y is the cosecant of u, and u is 4x squared. Okay, so I know then that dy, and I wanted to do one like this because these can be a little bit tricky when cosecant spits out more than one term, right? So it looks a little bit weird sometimes. So the dy du, what's the derivative of cosecant? It's a negative cosecant u cotangent u. Okay, you must put a u with each of those. And then what's the derivative of u with respect to x? That is 8x. Then my last thing I'm going to do is plug in where those u's are. I'm going to plug in that 4x squared. Let's take that 8x and put it in front. So I have a negative 8x cosecant then of 4x squared cotangent of 4x squared. Okay, this, you guys, is the derivative of the outside with me leaving the inside. So when I say leave the inside, I'm being a little bit lazy. When I say leave the inside, what I really should be saying is I should be saying take the derivative of the outside and evaluate it at that inside function. Okay, so that's really what I mean. I want to do one more. I keep saying I'm done, but I don't want to be done. These are really fun. One more example. Let's find, again, dy dx for something like this. Let's say I have y equals cosine cubed of x plus e to the x. This one's cray. Look at this. Cosine cubed of x plus, I can make this better, e to the 4x. Yeah. Okay, you guys, so the first thing I'm going to do is cry a little bit. Then I'm going to pull myself together, right? And I'm going to realize that I am a smart person. Well, smart has really nothing to do with it. I can figure this out. I'm a thoughtful person. I can do this. So I'm going to rewrite cosine cubed as the cube. And if you notice, we have like 1, 2, like 3 maybe chain rules going on here. So let's see, so let's kind of figure that out. My biggest outside function is something cubed, okay? Then I have this inside function. And then inside this inside function, I have another inside function. And then actually inside that inside function, I have another inside function. This is going to be so fun. This is the way we'll end it with this. This is a great time. I should probably go check on my daughter. She has had the iPad now for quite some time. So this is going to be, okay. So there's my outside function. Do you see that? There's the derivative of my outside function, right? I brought the 3 down, I took 1 away, and then I evaluate that derivative at the inside function. I leave the inside function alone. Okay, I'll rewrite that here maybe in a minute. Now I have to multiply by the derivative of the inside. So the derivative of the inside function right here, right? Again, we have a chain rule. What's the outside function for this inside function? My outside function is cosine. So the derivative of cosine is a negative sign. Leave the inside. That would be x plus e to the 4x. Okay, there's the derivative of this inside function. Okay, so I take the derivative of the outside and leave the inside. And now the last thing I need to do is I have to take the derivative of this inside function right here, multiply by the derivative of that inside function. So what's the derivative of that inside function? The derivative of x is 1. The derivative of e to the 4x. Remember, you rewrite it and then multiply by the derivative of the exponent. So that's going to be 4e to the 4x. This is a great one. Let's kind of move this stuff around a little bit, and then I promise I'll be done talking. We're at 45 minutes, so you guys, maybe you're not even watching anymore. Who knows? So I'm going to put the negative out. This is going to be a negative 3. I'm going to put the sign first just because it's not being raised to anything. X plus e to the 4x. Okay. Then I have this guy squared, so that'll be cosine squared of x plus e to the 4x. And then this whole thing is being multiplied by 1 plus 4e to the 4x. I probably would have put that 1 plus 4e to the 4x in the front had I thought about it. Whew. I need to go get some more coffee after that one. Or maybe something stronger. Just kidding. Just kidding. That was a joke. It was a joke. It's 12:30 in the afternoon. I don't think that's happening. All right, you guys, I hope that makes sense. This assignment won't be due on Friday just because I had a miss today. And on Friday, we'll do the fun sheet. I'll answer any questions you have about the chain rule. We will start 3.8 on Friday. But I do, we'll spend the first half of the class, of course, talking about any questions you have about the chain rule. You have to practice this guy. This chain rule is not going away. We're going to be using it for the remainder of the semester, and we're going to be using it in Calc 2 going backwards. So please practice it and let me know if you have any questions.